Hello everyone! In today's video we are going to finish talking about conservative forces. This is a topic which we have been covering in the last videos. In the previous video we have been talking about a more intuitive way to understand conservative forces. So I strongly recommend you to watch all of them before moving to this one. This is going to be the last video of this topic. Anyway, we can make a very briefly review of of the previous videos. In the previous videos, we talked about decomposing any general pattern of forces into two different cases scenario. One of them is a case scenario in which each component of the force depended only on the rest of the components of the position, but not on the own one. I mean, the x component of force depended on y, and the y component of force depending on x position. And a second case scenario in which the x and the x component of the force only depending on the x position, and the y component of the force only depended on the position in y. The combination of these two was is the as the result the general case scenario, the general pattern that any force can follow. I'm not going to explain much more about this. I recommend you to watch the previous videos to understand this much deeper. The only thing before moving to the second point is that only the left case scenario was that was the only one that was considered important to determine if a force is conservative or not. The right one didn't have any influence. Again, if you want more information about this first point, I recommend you to watch the other videos, okay? But in today's video, I would like to apply a more mathematical approach to explain something more general, because a conservative force is basically something very specific into something more general. That more general thing is basically the potential function. And in order to explain that, we are going to change the approach. We are going to apply here a more mathematical approach. So in this point 2, we can forget about physics for now. Then we come back to physics at point 3. So imagine that here we have a function, whatever function. Here we have a two variable function, but it could be a 1, a 3, or a 5, or whatever number of variables function. So if you have some function like this, how can we take the expression that give us the a very tiny increment of that function? Well, this, by making the partial with respect to the x and making the partial with respect to y, and multiplying by dx here and dy here, we can get this expression. This expression is actually the expression of a tiny increment of that function f. Okay? So that term here is the partial of x with respect to x, and that's the partial of x with respect to y. This function, this function is the potential function of that differential expression. Why? Because when we talk about differential expressions, what we basically have is a function here times dx plus another function here times dy. In the case we are working in a 3D case, we will have here plus another function times dz. So what does it happen in a case like this? Well, that is the potential function of that differential expression, because that differential expression, we can build that, or we can get that from differentiating the father function. I mean, this differential expression comes from this function, the father function, which is more rigorously called potential function. And this idea of potential function is quite important to what we are going to see later. But now just get that idea, okay? If you take any function, like for example this one, you take the partial with respect to x and you differentiate with respect to y, you will have 6 times x. That is the second derivative of f with respect to x and then to y. I mean, if you take the derivative of the partial of f with respect to x and you differentiate with respect to y, you have something like this, and it's 6 times x. If you want to calculate this, the second derivative with respect to y and then with respect to x, what you have is something like this, which is the partial of f with respect to y, and then you differentiate with respect to x. The result is the same, 6 times x. And this is not a coincidence. For whatever function you have here, for whatever function, this condition must be fulfilled for whatever function. Why? Because when you are differentiating, making the partial with respect to one variable, you are considering the other as a constant. So you differentiate with respect to one and then with respect to other, and here you are doing exactly the same thing, but in the inverse order. But the result is actually the same for whatever function you apply this. So here you can see that the differential form of this type, again, here is for 2 dimensions and this is for 3 dimensions. But if you have a differential form like this, how do we know that this differential form, this is a whatever differential form. We can have whatever function here plus times dx plus whatever function here times dy. So how do we know that differential forms comes from differentiating a further function or potential function? How do we know that? Well, knowing that a function, when you differentiate twice and you compute the second derivative, cross derivative, these two derivatives must be the same for whatever function. If you want to check to prove that this differential expression comes from differentiating a function, to prove that we need to check this condition. P is the derivative of f with respect to x, and q is the derivative of f with respect to y. So if you take that p function and you consider that as the derivative with respect to x and you differentiate with respect to y, and you do the inverse thing for the function q, you differentiate with respect to x because q is already the partial of f with respect to y. If the result of these two is the same, that means that that p function is the derivative of f with respect to x, and that q would be the derivative of f with respect to y, and therefore this differential expression would come from a further function or a potential function. Is that clear? If you have any problem or whatever, you can tell me in the comments, right? That is the idea. That is the idea, more general idea by applying a mathematical approach. What about point 3? Here in the point 3, I would like to explain you the relationship between the general idea I just explained you with the specific case of conservative forces, because you may wonder, okay, we know we have the idea of conservative forces, no. The idea of the potential function and the mathematical approach you have already done. But what is the relationship between that mathematical approach and the specific case we have been dealing previously in the other videos about conservative forces? Before explaining that, let me explain some concepts very briefly, okay? First of all, in physics, work is the same, is equal to minus the difference in potential energy. In physics, when in some scenarios in physics, like for example, when you have a ball here with some distance with respect to the floor, the energetic situation of that ball can be partially described with potential energy. It's the energy associated to the position or location of a body. So the higher it is, the more the potential energy will be of that ball. The same happens here with the restoring action of the spring. If you change the position of the ball, you are changing the potential energy of the system. So if a field is conservative, that means that the potential function that it comes from, I mean the potential energy function, only depends on the point at which we are located at. So if you start here and you want to move the particle from here to here, this initial point is associated with an initial potential energy and this endpoint to an end potential energy. So the work done is going to be associated with that difference in potential energy, and we would only have to consider the initial and the end point. So what is the mathematical definition of work? Is the integral of the dot product between F, the force, and a differential vector anywhere, any general differential vector, leading us to this expression like this. But what about if instead of moving at any direction, we move a very tiny step to within the x direction? The only component of the force that in that direction would make some work is the x component of the force, because the y is perpendicular to the x, and it doesn't make any work here if we move a tiny amount within the x direction. So if that is the work that the force, some generic force does within the x direction, the x component of that force is something like this, the partial of work with respect to x. The same applies when we move just a little amount within the y direction. By moving a little amount in the y direction, we can get the value of the y component of the force, something very similar to here. So knowing that we can describe the situation, the energetic situation of a body in physics by using potential energy, if you take that function, the function of potential energy, and you differentiate twice, first with respect to x and then with respect to y, and developing this a little bit more, we can see that this go from this to this, and from this we go to this. The difference, I mean, if you remember, work is minus the difference in potential energy, so that difference in potential energy is minus the difference in work. The derivative of work with respect to x is the f sub x, the x component of f. Differentiating that with respect to y, we have that derivative. Something very similar applies when we apply the inverse case. I mean, you differentiate first with the potential energy with respect to y and then with respect to x, leading us to this expression here. So, since for whatever function, and of course also for functions of potential energies, this must be exactly the same than this, and this is this, and this is that, this must be this. And the negative signs cancel, leading us to that expression. And that is the explanation, another explanation of why a conservative force must be described, or the condition that it must meet is something like this. So I hope it's everything clear about this topic. So if you have any problem, just tell me in the comments. With all that said, see you in the next video. Bye.